Hello everyone, this video covers sections 11.1 through 11.3, maybe 11.4. 11.1 is about sequences, which is something you have seen before in precalculus. And then from 11.2 on, everything is about series, which technically a series is just the sum of all the terms of a sequence, but we'll get to that once we get to 11.2. So first we're just gonna review what sequences are, and you saw this in precalculus or something very similar. So let's start with the notation. A series is usually denoted by this, A1, A2, A3, and so forth. So these are the terms. Sometimes it's just written like this, AN. Or if you want to be more specific, you will say AN, where n is equals to 1 to infinity. By the way, n doesn't have to start in 0. It could be starting 1. It doesn't have to start in 1. It could start in 0, minus 1, minus 2, or whatever. The only restriction is that the domain has to be integer. Okay, so n has to be an integer. That's the only difference. Okay, so you cannot have like the 1/2 term. This doesn't make sense for sequences. Now, the most common sequences you see in precalculus are arithmetic sequence, geometric, and Fibonacci, but mostly everything focused on arithmetic or geometric, and geometric is going to be the most common one we're going to use. Remember, arithmetic just means you add the same value to get to the next one. Like this is the most basic arithmetic sequence, which means you just add 1 to the previous value. You can have this one, 2, 4, 6, 8, which means you're adding 2 to each value. Geometric, it means you multiply by the same value to get to the next one. So you have 1, you multiply by 3, you get 3, times 3 is 9, times 3 is 27, times 3 is 81, and so forth. So this is what geometric is. Same thing, you can have time. You can start with 4, you multiply by 1, 4, you'll end up with 1, then 1, 4, 1, 16, and so forth. So then this will be considered A1, A2, A3, A4, A5, and so forth. Same thing here, A1, A2, and so forth. Now the Fibonacci sequence is just a special case. This one you start with 1, 1, and then you add the previous two values. So 1 plus 1 is 2, 2 plus 1 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so forth. So this one is found in nature a lot. Okay. Now, to continue with the more notation, we're going to use the words convergent and divergent. Now, since we're going to use this many times, I want to write this for convergent. That will be the lazy way to write it, and this for divergent. So convergent, it means that you can think as settles to a value, and the value has to be finite. And divergence obviously means not convergent, which means either doesn't settle to a value or keeps changing values all the time, but it doesn't settle to anything. Okay, so for example, this one is divergent because this one keeps going to infinity. Same thing for this one. This will also be divergent. Okay, same thing here, but this one will be convergent. Why? Because notice the numbers are getting smaller and smaller. This actually converges to 0, and this one goes to infinity. That's why it's divergent. Same thing here. It goes to infinity. Now, the sequence doesn't have to go to infinity to be divergent. You can also we can have an example of a geometric sequence where you multiply by -1. So notice this keeps changing from -1 to 1. So therefore this will be divergent because it doesn't settle to a specific number. Okay. So obviously if it goes to infinity, it's going to be divergent, but if it doesn't settle to a specific number, or if it oscillates between 2 or 3 values, it's also not convergent. Now let's look to the official definition of convergence in terms of limits. So a sequence has a limit L, and we write the limit as n goes to infinity of the sequence is equals to L. So this is very similar to the definition of limits during calculus 1, or you can write it this way. And then this is what I told you about convergence and divergence. If we can make the terms an as close to L as we would like by taking n sufficiently large, which means the limit exists is not infinity, we say that the sequence converges, otherwise the sequence diverges. Okay? So let's do a couple of examples. For this one, if you remember calculus 1, the limit as n goes to infinity, since they have the same degree, all you have to do is divide the coefficients of the biggest degree, which in this case will be 6/9, which is greater or less than infinity. So that implies this one is convergent. That's it. Now, one of the most famous limits from calculus was this, and you should remember this for the rest of your lives technically. So recall that the limit as n goes to infinity of 1 plus 1 over n to the n power is equals to e. Okay, so this is a very famous limit, and everybody should remember this forever pretty much. Or in general, this is a constant a, this will be e to the a. Okay. Well, why is that important? Well, we're going to use that one for this problem right here. So they don't look the same, but what we're going to do is this. Notice that this is the same thing as n plus 4 over n to the negative n. Now, why is that the case? Well, notice this, 2 over 3 squared, which clearly is 4 over 9, is the same thing as 3 over 2 to the negative 2. You should check that, okay? Because we're going to use this trick multiple times. Right, well, notice that then you can rewrite this as 1 plus 4 over n to the negative n, which is the same thing as 1 over 1 plus 4 to the n to the to the n power. But using this identity, this one approaches to 1 over e to the 4 as n goes to infinity. Well, since this is less than infinity, obviously, so this is convergent. Now, another classic limit to recall from calculus 1 is the following, that the limit as n goes to infinity of n to the a over n is equals to 1. Again, I highly recommend you to memorize these limits and check the calculus 1. Why is this true? This is actually true because of L'Hopital's rule. Okay, but just in case that you forgot it. So therefore here, clearly then the limit as n goes to infinity of a to the n is going to be equals to 1, which is clearly less than infinity. So therefore that implies this is convergent. And finally, another limit to recall was this, that the limit as y goes to 0 of some y over y is equals to 1. You can also use L'Hopital's rule to check this is the case. So now notice that this doesn't look the same, but if you rewrite it like this is the same thing as sine of 1 over n divided by 1 over n. And also notice, okay, that as n goes to infinity, 1 over n goes to 0, which means you can use this formula. So therefore the limit as n goes to infinity of sine of 1 over n divided by 1 over n is the same thing as this limit exactly, because this goes to 0, and clearly this one goes to 0. So the limit is 1, which is less than infinity, so therefore this is also convergent. Now the last thing for section 11.1 is the concept of being bounded or a bounded sequence. So this is what we have. A sequence is bounded above if there is a number m such that all the values for the sequence are less than equals to capital M, and is bounded below if the value for an is bigger than all these values. I mean, if all the values for an are bigger than n. Now, if the sequence is bounded above and below, then we say we have a bounded sequence. Okay, so let's look to this example and see what's happening here. So let's say that n is equals to 0. So notice that an, you can also rewrite it as cosine m pi over 2 to the n, okay? Because this will make it easier to see what's going on. So therefore this is equals to that. So what happens if n is 0? If n is 0, a of 0 will be cosine of 0, which is 0. I mean, cosine of 0 is 1, and this will be 2 to the 0, which is 1. So the answer will be 1, okay? So let's do a graph. So I have 0. So you have 1 here. So that will be the first value. Now, what about if n is equals to 1? Then we have a 1. Then it will be cosine of pi. The cosine of pi, remember, is minus 1. So it will be 2 to the 1, which is 2. So you're going to go from 1, and then let's say this is negative 1, to minus 1/2. Now, what about if n is 2? Then this will be a 2, which will be now cosine of 2 pi, which is 1. But now this will be 1/4, which will be here. So notice how this goes from positive then to negative to positive. It's gonna keep going to negative, but you can see that this is approaching to 0. So clearly this one will be convergent. So now let's see if this is bounded. So notice the cosine of m pi divided by 2n, that this is always going to be less than equals to 1. Why? Because this is changes from negative 1 to 1. This is the biggest it can be, and this is always 2 over n, which will be 2, 4, a, and so forth. So this is clearly less than 1. So therefore this is bounded above by, this will be capital M. And also a n is also going to be bigger or equals to negative 1. So therefore this is also bounded below. So this will be lower m. So clearly this is bounded. Okay. Now notice, so as a note, if an was equals to just cosine and pi, then this will be divergent. Why? Because it will go from 1 to minus 1, positive 1, negative 1, positive 1, negative 1, and so forth. And we already know that this doesn't converge. The reason why this one converges is because of the 2 to the negative n. Okay. All right, what about this one? So let's do a few. A of 1 will be 2 plus negative 1 to the 1 over 1. Remember, notice how you cannot use 0 here because you will be dividing by 0 and that's not allowed. So therefore, this will give you 2. What about if A is 2? It will give you 2 plus negative 1 squared over 2, which will be 2. Oh, this is 2 minus 1, which is equals to 1. It will be 2 plus 1 half, which is at 2.5. What about if n is 3? It will be 2 times negative 1 q over 3, which is 2 minus 1 third, and this is equals to 5 over 3. So you can see that if this is even, it's going to increase it, and is going to decrease it. For example, you wanted to find a 10, it will be 2 plus minus 1 to the 10 divided by 10. So then it will be 2 plus 110. But in either case, this is as big as it's going to get. Okay. So therefore, from here, we can say that an is going to be less than or equals to 2.5 and greater or equals to 1, because this is the smallest it will get. So this will be the lowercase m, is capital M. So therefore, this implies this is bounded. Now the question is, this convergent or not? Well, the limit as n goes to infinity of 2 plus minus 1 to the n over n. Notice that this one goes to 0, so this is just 2, which is less than infinity. So therefore it's convergent. Okay, one final note about sequences. So here is the note: every bounded monotonic sequence is convergent. Okay, so what does monotonic means? Monotonic means that it's either increasing or decreasing. Okay. So if you have this type of sequences, then they will be convergent. All right, so that's it for sequences. We're gonna go now to 11.2, which for now on it will be all about series. All right, so 11.2 is series in general. After that, each section has some specific kind of series, but this is the notation for series, and this just means technically you add all the value of the sequence. Okay, so make sure you distinguish between sequence and series. So remember, these are the values for the sequence, but if you add all the values, then it's called a series. Okay. And if the sum is less than infinity, then it will be called convergent. And if the sum is infinity, it will be divergent. Okay. Now, in pre-calculus, like I say, you have already seen geometric series. So recall geometric series from pre-calculus. So you have a geometric series, the sum was equals to a1 over 1 minus r. Now, how do you know this is geometric? Well, there's a typo here, so this should be 1. So notice the 1/3 times 1/3 will give you 1. 1/3 times 1/3, I mean 1/9 times 1/3 will give you 1/9 and so forth. So here this is geometric with r is equals to 1/3, and this equals to a1. So therefore the sum is going to be a1, which is 1/3, divided by 1 minus 1/3. So it will be 1/3 divided by 2/3, which is equals to 1/2. So therefore, if you add all the values, it will give you 1/2. All right, now let's look to this one. You can break this into two pieces. This will be 1 to infinity of 3/5 to the n, plus 2 the sum from n equals to 1 to infinity of 1/n. So now for this one, notice that you can rewrite this as the sum from n equals to 1 to infinity. You can put the 3 in front, and then this will be 1/5, the whole thing to the n, and then it will be 2 and to 1 to infinity, and this is 1/n. You can see that this is geometric. This one is not geometric, and here the value for r is 1/5. Remember that this will be conversion if the absolute value of r is less than 1, which it is the case here because r is 1/3. Here r is 1/5, so therefore this part is convergent. Now we're going to be looking to this series a lot, 1/n, and 1/n is called the harmonic series. And if you actually remember to remember section 7.8, the improper proper integrals, remember that the integral of dx over x from 1 to infinity was equals to infinity, and therefore this was divergent. So therefore the harmonic series is divergent. So now here you have a combination of two series. If the first one is convergent, the second one is divergent, the whole thing will be divergent. Okay, so both of them have to be convergent to be convergent. And we'll talk more about the harmonic series later, but this is the best way to look at it right now. If you integrate 1/x, remember the integral is infinity, so therefore the series is divergent. Now note something that's going to be very, very, very useful, and people confuse the meaning of this all the time. There's something called the divergence theorem, and this is something that you need to remember for the rest of the class. And the divergence theorem says the following: if an doesn't, or let me write it in terms of limit, if the limit as n goes to infinity of an is not equals to 0, then automatically that implies that the series is divergent. Okay, the opposite is not true, meaning if the limit is 0, it doesn't mean that it's convergent. And this is the perfect example. Notice that the limit as n goes to infinity of this is 0, but this is divergent. So if the limit is not 0, then you can say it's divergent. But if the limit is 0, it doesn't mean it's going to be convergent. Okay. All right, let's look to this one. There's a typo here. This one should be negative. This is called a telescoping series. This is a special case. So let's see what happens and why it's called telescoping. So this one starts with n equals to 4. So notice this is what we will get. If n is 4, this will be 1 over the square root of 4 minus 1 over the square root of 5. And then you move to the next one. it will be 1 over the square root of 5 minus 1 over the square root of 6, and so forth. To the last one is going to be 1 over, let's say, the square root of j minus 1 over the square root of j plus 1. Okay? So this is what is called a partial sum. So then notice that this one will, the first one doesn't cancel, but this will cancel with that one, and so forth. So the only one you will have left will be this one and this one. So therefore, the partial sum, which is denoted by Sj, is going to be 1/2. Remember that this is equals to 1/2 minus 1 over j plus 1, because those are the only two terms that remain. But as j goes to infinity, notice that this is equals to just 1/2, which is less than infinity. So that implies that the series, the original question, this is going to be convergent. Okay. Now notice, and this is very, very important to realize, that we don't know what the sum is. We just know it's less than infinity. The only one so far where you can actually find the sum is the only one you can actually find the sum is for the geometric series, which brings us back to this question right here. This one will say for which value of x is this going to be convergent. Okay, so for which value of x is the series convergent. So is the series convergent? So that's a question. So if we identify this as geometric, okay, so we know that a geometric series, it will be convergent if r, in the absolute value of r, is less than 1. So therefore this will be r, so we'll have r is equals to x plus 2. So then the absolute value of r has to be less than 1. If you solve for x, you will have minus 1 less than x plus 2 less than 1. So that implies minus 3 is less than x less than minus 1. So these are the possible values for x. We're going to see this kind of series in a lot of detail in, I think it's 11.7a and 9. And when you involve the x with the n, these are actually called power series. Now the next question is asking exactly the same thing. So notice that we can rewrite this as a geometric series. Again, this will be sine of x over 3 to the n. So therefore the value for r is sine of x over 3. And if we want r to be less than 1, so that implies that the absolute value of sine x over 3 has to be less than 1. But for this particular case, remember the absolute value of sine of x is always less than 1. So therefore we know the sine of x over 3 is always less than 1. So therefore this implies the sum is convergent for all values of x. Right, so far in 11.1, where we talk about sequences, and then in 11.2 we start series, and from now on everything's going to be about series. In 11.2 we talk about series in general. Remember, to be convergent, the sum has to be finite. And from now on, we're going to have a specific test to check if whether the series is convergent or not. So the first test we're gonna talk about is called the integral test, and that's gonna be section 11.3. All right, so in this section we're gonna use the integral test, which, like the name says, we're gonna integrate to determine whether a sequence is convergent or not. I mean, a series. So suppose f is continuous, positive, decreasing function between 1 to infinity, and then if we define the sequence to be of this form, then the series is convergent if and only if the integral is convergent, meaning that if the integral is convergent, then the series will be convergent, and if the integral is divergent, then the series will be divergent. Now, before we do the official examples, so note, and we did this in section 7.8 when we talk about the improper integrals. Remember that they are the integral from 1 to infinity of 1 over x squared, and you should check this that this was less than infinity. So that implies that the series 1 to infinity of 1 over n squared is convergent. And in the last section we just did this one, the integral from 1 to infinity of 1 over x dx, this is equals to infinity. So therefore that means that the integral from that the series is divergent, and this one even has a special name. Remember, this is called the harmonic series. Okay? So this is what the integral test does. So you just integrate, and the integral is finite, then the corresponding series will be convergent, if not is divergent. All right, so for this one, notice that you have to check that the function is positive, which it is, and that is decreasing, which it is. So therefore here we need to find the integral from 1 to infinity of dx over 3x plus 1 to the 4 power. Okay? So we need to make a substitution. This is 3x plus 1. So the u will be 3 dx. And notice that if x goes from 1 to infinity, then here we will need 1/3. The integral now will go from 3 plus 1 is 4 to infinity, and this will be du over u to the 4. Then if we integrate this, this is 1/3 times negative 1/3 u to the minus 3 from 4 to infinity. So this is equals to minus 1/9 times 1 over u cubed from 4 to infinity. So notice this will be minus 1 over 9. If you apply infinity here, this will give you 0. And then it will be minus 1 over 64, which clearly this is less than infinity, so that implies that is convergent. So therefore that implies this one is convergent. Now pay a lot of attention to this problem. This is going to be very, very important, okay, for the future. So notice here that if we use the integral test, we're going to have the integral from 1 to infinity of 1 over x to the p dx, which is the same thing as 1 of the integral from 1 to infinity of x to the negative p dx. And if we integrate, this will be x to the negative p plus 1 over negative p plus 1 from 1 to infinity. So this is the same thing as 1 over, I'm just going to write 1 minus p, and then there will be x to the minus p plus 1 from 1 to infinity. Okay, so notice, okay, that if you have 1 over, let's say, x to the 4, this clearly goes to infinity. This clearly goes to 0 as x goes to infinity, okay? But if you have x to the 4, well, this goes to infinity as x goes to infinity. So therefore, this is the case that you want. Okay? And notice that this one, you could write it also like this, x to the negative 4. So clearly x to the negative 4 goes to 0 as x goes to infinity. Okay, so again, this is the same thing. The condition is that the exponent here has to be negative. So therefore, if you want this to be convergent, then you need minus p plus 1 to be negative, which means minus p has to be less than negative 1, or p has to be more than 1. And this is what is called a p series. So this will be convergent if p is more than 1, and therefore this will be divergent if p is less than 1. Okay, actually less than or equals to 1. If you look to this, you can see clearly that this is a p series. The value for n is 1, so that's why this was divergent. Here the value for n is 2, which is more than 1, so it's clearly convergent. So from now on, you can just use the result and solve the problem. So for example, you have this, and I say n to the 1/2. Well, clearly this is going to be divergent because p is equals to 1/2, which is less than 1. That's it. So that's how easy it will be from now on. Right, what about this one? Well, we need to integrate well, we had to calculate the integral from 1 to infinity of x over x to the 4 plus 1 dx. So here we're going to make a substitution. Let's say u is equals to x squared. So the u will be to x dx. So this will be 1/2 the integral from 1 to infinity of du. This will be u squared plus 1. So this will be 1/2 tangent inverse of u from 1 to infinity. So this is 1/2, and then tangent inverse of infinity, remember, is pi. Also remember that all of this implies that we're using limits, and then minus tangent inverse of 1. Okay, so this is 1/2 times pi over 2 minus pi over 4, because remember tangent of pi over 4 is 1. You don't really have to compute this. All you need to know is that this is less than infinity. So that implies that it is convergent. So therefore this is convergent. From now on, you always have to say y is convergent. So this is convergent by the integral test. Yep. Well, now let's try this one with let's say p is equals just to 1 for now. And you can try this on the homework in general. So here we want to find the integral from 1 to infinity of ln x over x dx. So here the substitution will be u equals to ln x. Du is dx over x. So this is the same thing as the integral from 1. ln of 1 is 0. So this will be 0 to infinity of u du. So this will be 1/2 u squared from 0 to infinity. So this 1/2 of infinity squared, which clearly is infinity, minus 0. So the whole thing is infinite. So clearly this is divergent. But what about if p is equals to 2? So just give it a try, and then on the homework we can do this in general for p. once we do this in class. And that's it for now. We'll talk about the remainder term in the next video. So that's it for 11.1 to 11.3.